Hi everyone, welcome back to Math 112. This is Scott. Let's get started. What we are doing today is continuing the project of Chapter 8. And Chapter 8's whole purpose is to take the trigonometry that we already developed and extend it into new terrains. And here, what we're going to be talking about are vectors. Alright, so mathematical values come in two main categories. Scalars, and these are things that can be expressed by just a simple number. So these are quantities expressed as a simple number. And examples of this would be answers like how many. So examples of these would be things like maybe population. Also, an example of this would be something like speed. Another thing that would be expressed as a scalar would be energy in physics. Another thing would be mass. However, there is another category, which is vectors. And vectors are quantities that cannot be expressed as a simple number, but rather have to be expressed as a couple of different components or as a magnitude and direction. So these are quantities that require multiple components. Or magnitude and direction. So these either require you to specify multiple different, basically coordinates, you might even think of them, or else you need to say how much and in what direction. And examples of this would be, instead of speed, there's the related but slightly different physical quantity velocity. Momentum, force, or weight, which is another form of force. So these are all slightly different quantities from their scalar counterparts, and they require you to also specify the direction of action. So the difference between velocity and speed in physics is that speed is just some number that represents how fast you're going, whereas velocity represents how fast and in what direction. Momentum is a measure of how much your mass times your velocity is. Force. So a force is always applied in a specific direction. Weight is specifically the force caused by gravity that pulls something to the ground. All right. Now we can represent vectors two ways. So there is a graphical representation And then there's an algebraic representation. So graphically, and then what we just do is you just draw an arrow. So typically a vector is represented by an arrow. So graphically, just draw an arrow in a certain direction with a certain length. So it just looks like this. And the way we label vectors is with letters such as V, W, sometimes U, depending. And you indicate a vector by putting a little mark above it. So notation. Vectors are given extra markings such as we write like V with a little arrow, or maybe we write this as a specific vector. We'll discuss it in a second. You put like a little, it's called a hat. It's a little carrot-shaped thing. And then every once in a while, so this is more like a physics notation, we won't do it, but you could underline it. For example, and in print, these extra diacritical marks aren't put. Instead, books use a bold typeface for vectors. In print, use a bold typeface for vector quantities. And an italic typeface for scalar quantities. So in print, vectors are denoted by not being italic and by being in bold. Scalar quantities, on the other hand, are typically represented with italics. So graphically, we can represent them that way. And then there's also an algebraic notation. So graphically is this, or algebraically, there are two main formats that we're going to use, and then there are some other formats that are sometimes used in other contexts. We can either list the components in angle brackets, for example. We might say V is equal to, and then you give here an angle bracket and then a number like 1, comma, -2, for example. Or we can write the horizontal component and vertical component as coefficients of the standard unit vectors, and I'll explain what all this means in a second. I, which is the horizontal, and it's written not with a dot but with a little caret, and j, and that represents the vertical. So then here v would then look like 1i, which we would not write the 1, just like we would ordinarily not write a coefficient of 1 unless we absolutely had to, and then minus 2j. Now, the important thing about vectors that distinguishes them as important quantities is that they can be manipulated in two ways. They can be added slash subtracted from each other, and they can be multiplied by scalars. So vectors can be added or subtracted with each other, or multiplied by scalars. Now, what this means is easiest to see graphically and then very easy to do algebraically. So graphical representation. Graphical representation of vector arithmetic. So first off, addition. So v plus w. So this represents the new vector that you would get by taking first v and then on top of that also w. And the way that works is like this. So represents the new vector formed by putting v and w head to tail and drawing a new vector that goes straight from the beginning to the end. So for example, let's say v is going like that. So up and to the right and is that long. And let's say w is maybe that long and it's just going straight to the right. So then v plus w. So then v plus w, this would be v plus w, so this would be first draw the v, and then draw the w, starting at the tip of the V here. So this would be V, this would be W, and then this would be the new vector that goes straight from the start to the end. And so V plus W will be going like that. And so the important thing about it is the length and the direction, as indicated by this. It's a little bit easier on graph paper, and what you'll have to do on Pearson is just identify out of the various diagrams chosen which one properly represents the addition of the vectors. Now, scalar multiplication is accomplished by just essentially scaling the vector by whatever the corresponding number is. That's why it's called a scalar. So scalar multiplication, if we have A times V, so notice A does not have the little vector quantity on it, or the little vector indicator. So this represents V multiplied by, or let's say amplified or scaled by A. Scaled by a factor of A. So for example, let's say V is something like this. Then 2V would just be the same thing as V, but twice as much. So scale it by a factor of 2. It's like 2 copies of V, like V plus V, just like with numbers. So it's essentially like 2 copies of V head to head. 1/2 V would be the same thing as V, but only half as much. So instead of scaling it up by a factor of V, or by a factor of 1/2, it's scaling it down. So it's the same thing as V, just half as long. Now, if the scalar is negative, the vector's direction is reversed. So for example, negative V, which would mean just like negative 1V. So it's the same thing, except the arrow is now going the other way. Negative 2V would be just like this, but twice as long. And then there is vector subtraction. So vector subtraction, the easiest way to think of it is as adding V plus negative W. So V minus W represents V plus negative W. So if V is going like this, and let's say W is going like this, then essentially we can just break it down into 2 parts. So then negative W would be the same thing, but in reverse. So it would be going to the left instead of to the right. And then that means that V minus w, which is the same as v plus negative w, would represent going first in the direction of v, then in the direction of negative w, and then going from beginning to end to form the new vector v minus w. So v minus w, then, if we wanted to write it like that, would be going approximately that much, and in that direction. Just as a note, there's another way classically that vector subtraction is represented, and that would be put v and w tail to tail and go from the tip of w to the tip of v. But that way is very easy to mess up, so this is the way that I will officially endorse. Now, graphically speaking, it's all very fun, but it's not very easy to get firm answers out of things when you're trying to get an answer to a mathematical question. And so when we want to do it algebraically, what we just do is we take the components and we do whatever the thing is, whether it be vector addition or scalar multiplication, and we do it component by component. So just do the addition or scalar multiplication component by component. So for example, if v is equal to, let's say, 3 comma negative 2, so that's a 3 for the first component, negative 2 for the second component, then if w is equal to 1, 5, then v plus w would just be 3 plus 1 for the first component, negative 2 plus 5 for the second component, which would just be 4 and then 3. 2v would just be 2 times 3 and 2 times negative 2, which would just be 6 and negative 4. Put C over here. And then if I wanted to do something like v minus w, I would just do the same thing, component by component. 3 minus 1 this time, and negative 2 minus 5. So it's going to be 2 comma negative 7. And then if I wanted to do something more complicated like 2v minus 3w, then I could just take this two pieces. I could take the two pieces individually and then combine the results, or I could be a hero and try to put it all together all at once. So 2v is equal to 2 times 3, comma 2 times negative 2. Oops, angle bracket, not parentheses. That'll be 6 negative 4, just as it was a second ago. 3w would be just 3 times the entries of w, so that'd be 3 times 1 and 3 times 5. So in other words, just 315. And then the grand result, 2v minus 3w, would just be 6 minus 3. Just take the two results and subtract them, and negative 4 minus 15. All right. And so then that's going to give us just 3, negative 19. All right. This also applies if it's written with the unit vectors. So let's also just as a quick check here, let's say that v equals 2i plus 0j. W equals, say, I minus 2j. So then, if we wanted to do 2v, that would just be 2 times 2i, which is just equal to 4i. Let's say I wanted to do v plus w. That would just be, 2 plus 1 I plus 0 plus negative 2 j. You can just take the coefficients and add them in usual algebra fashion. And that's how we would express it. 3i minus 2j. Okay. So now, if we are given the starting and end point of a vector, we can express it as a position vector, or it would be perhaps more appropriate to call it a displacement vector. Where the v is going to just equal change in the x times I plus change in the y times j. In other words, x2 minus x1, y2 minus y1. And the way this will typically look for you in your homework especially is you'll be given an initial point and a terminal point, and then you will have to find the position vector. So as an example here, let's say v has an initial point p equals, and then here this is just going to be a point, so it's just going to be coordinates. Let's say it's just going to equal negative 3 comma 2, and terminal point q, which will equal, let's just say 6 comma 5. express V in the form AI plus BJ, and that is, in other words, i.e., find its position vector. So the way this would go, it's just going to be x2 minus x1, so 6 minus -3, oops, and that's going to be the I, and then y2 minus y1, 5 minus 2, that's going to be the j, and then we just crunch the numbers and we get 9 I plus 3j. Now the meaning of I and j. It's easiest to see if we just look at it graphically on the xy plane. So draw V with its tail at the origin and its head just pointing that way. And if this is A and this is B, then basically what we're doing is we are breaking it into AI plus BJ. And that gives you the V broken into its two components. So I is a vector of length 1 that points horizontally, and J is a vector of length 1 that points vertically. And then what that means is that the component that is attached to the I will represent the x coordinate of the final point, and the component that is represented by the j will represent the y coordinate. So then if v equals ai plus bj, this corresponds to a vector whose tail is at the origin and whose head is at the point AB. Now, what this means is we can express vectors in this sort of a format by giving them the x-coordinate and the y-coordinate essentially of where they end up, or we can express them in a more polar form. So we can use the same approach as polar coordinates to represent the magnitude, i.e. length, and direction, i.e. Angle. Of a vector. So the notation that we use for the magnitude of a vector is very similar to the absolute value sign. The magnitude, in other words, the length. So this corresponds with the r from polar coordinates. And first off, the notation. Use just like a double barred absolute value. This represents the magnitude of v, and this corresponds to r in polar coordinates. So what that means then is, so if v is equal to ai plus bj, then the magnitude of v is the same as the square root of a squared plus b squared. A squared plus b squared. And what we've just got here is a classic Pythagorean identity, or the Pythagorean theorem even. So if we were just talking about the lengths of these, A and B would be the lengths of the two legs, and then the magnitude would be the hypotenuse. Let's try an example of something like this. So find, for each of the following, find the magnitude of V. Simplify any radicals. All right, so as an example here, let's just go with, to start with, V equals 5i minus 12j. Well, in this case, a equals 5, b equals negative 12, and so the magnitude of v is just going to be the square root of 5 squared plus negative 12 squared. Careful about parentheses when you've got negatives involved. And that's going to be the square root of 25 plus 144, which is the square root of 169, which, as it turns out, happens to just equal 13. It's a perfect square. By now, hopefully you've seen it enough times with a 5, 12, 13 triangle that you recognize it. Sometimes it'll come out in a nice perfect form like this, sometimes it won't. Alright, how about a vector like this? V equals 3i minus 2j. Well, once again, you can just figure out what the a is. A is 3, b is negative 2, so then the magnitude of v will just be, according to the Pythagorean Theorem, 3 squared plus negative 2 squared, which is going to be 9 plus 4, which is just going to be the square root of 13, which we can't simplify anymore. What about something like C? V equals negative 10j. So the I component is just 0. Well, if you untangle what this actually means, it's very clear actually what the length of this has to be once you draw the picture. But you don't even need to draw the picture, you don't need to think about it, you can just use the same old formula and it will give you the same valid answer. So 10 squared, so negative 10 squared becomes positive 100, which just will equal 10. And that, of course, is exactly what it should mean, because this is saying that the vector is pointing purely in the y direction, 10 units, and so we can see that the length would be 10. And then D, let's say we had something like V equals 5i and negative 5i minus 5j. Alright, so a equals negative 5, b equals negative 5 as well, and then the absolute value, sorry, it's the magnitude, but you can also, it's also often pronounced the absolute value, is equal to square root of negative 5 squared plus negative 5 squared, which is just going to be 25 plus 25, which is actually going to be easiest for me to work with if I just express it as 25 times 2, and then I can break it up into two pieces. Square root of 25, square root of 2 is equal to 5 root 2. So simplifying radicals means doing things like that. Pull out any perfect square factor that you can find in it, and then that will then become a number in front of the radical. All right, now if we want to do more complicated vector arithmetic, we just have to do it piece by piece. So perform. Oops, perform. Just write it better. Perform. More complicated vector arithmetic piece by piece. So for example, evaluate. or I should say find. Find each expression. If v is equal to negative 5i minus 3j, and w is equal to, let's say, I minus j. All right. So the things we can have to find would be things of a relatively simple nature, like maybe just 2v plus 3w. So this is just a matter of taking the components and doing what you need to do to them and then combining those. So this is going to be 2v is going to be just 2 times each component of v, 2 times negative 5i, plus 2 times negative 3j, which would then be negative 3i minus 6j, 2 times negative 3. That's what that says. Okay, 3w we would evaluate in a similar fashion. So that's just going to be 3 times the 1. That was the original component of I, plus 3 times the negative 1. That was the original component of j. And that's just going to be 3i minus 3j. And then put them together. 2v plus 3w. It's just going to equal, just combine them component by component. Negative 3 plus 3 as the coefficient of the I, plus negative 6 plus negative 3 as the coefficient of the j. And that's just going to be 0. And then minus 9j. Now, if we are told to do something like v minus w, the magnitude of that, well, we just have to break it down into first the task of finding v minus w, and then the task of finding the magnitude of that. So v minus w, that would equal, so negative 5 for the first component of v, minus minus 1 for the first component of w. Oops, and that's going to be I, plus, and then just the components, just do subtraction piece by piece here. Negative 3 is the component on v of I, and then minus a negative 1 on the j. So negative 3 minus negative 1. And then that's going to be negative 6i. Negative 3 minus negative 1 really becomes like a plus, right? So then that's going to be like negative 3 plus 1, so it's going to be negative 2j. Okay, so then a will be negative 6. B will be negative 2. And now we have to find the magnitude. So the magnitude of v minus w is going to be the square root of negative 6 squared plus negative 2 squared. And that's going to be the square root of positive 36 plus positive 4 which is going to equal the square root of 40. Now here I can see that there is a perfect square in there. There may be more than one. I'm not quite sure yet, but I know at least it is that it has a factor of 4. 4 times 10. And so then I can see that this is going to be root 4, root 10, which is just going to be 2 root 10. And there's nothing more I can really do here. 10 doesn't have any more perfect squares in it. If my original perfect square were not the biggest perfect square that was a factor of the number there, then I would notice that by the fact that I would still be able to break out another perfect square factor of what was left. So that's how you would do something like that. And then maybe what we have is also something along the lines of this is C magnitude of V minus magnitude of W. So we just have to break it down into two pieces. First find the magnitude of V, then find the magnitude of W, and then subtract them. And these are just going to be a number minus another number. Okay, so V. So for magnitude of V, start with that. Okay, so A on the V was equal to -5. B was equal to -3. So then the magnitude of V is equal to the square root of -5 squared plus -3 squared, which is just going to equal square root of 25 plus +9 is equal to the square root of 34. Now you would look for a perfect square factor here, but there isn't one. Now as for W, that is equal to, or that gives us an A of, looking back at our original W, 1, B of -1. So then the magnitude of W is equal to the square root of 1 squared plus -1 squared, which is equal to the square root of 2. And so the overall result here, magnitude of V minus magnitude of W is equal to root 34 minus root 2. And you cannot put these together in any reasonable way. You cannot just add and subtract square roots willy-nilly. You can multiply and divide them, but you can't add and subtract them in a way that translates cleanly. All right. So that's the magnitude. Now, once we have the magnitude of a vector, then we can also then find what is called a unit vector that points in its same direction. So unit vectors. So unit vectors are vectors of magnitude 1. So the magnitude of a vector is 1. And we can find a unit vector that has the same direction as any given non-zero vector V. What I mean by non-zero is, non-zero vector V. What I mean by non-zero is V can't just be 0, 0. It can't be 0 times 0i plus 0j. So that would technically be a vector, but it would not be a vector we can find that has a direction, because it's just starting at the origin and ending at the origin. So it's not going any particular direction. Okay, so the idea is scale. Scale the vector by its magnitude. So in particular, u, which you can write with a hat or an arrow. Hats are usually used to represent unit vectors, or we use the letter u frequently also to represent a unit vector. So you basically divide by the magnitude, and you multiply that. And we can write, so we often write vector divided by its magnitude. And here, u hat represents a unit vector. As an example, we might have something like this. Find a unit vector u with the same direction as v. And here we'll have several different v's to choose from. Not supposed to be any kind of meaning to that underlining there. All right. So as a first one here, let's just take something like v equals 2j. So it has no I component. All right, well, first off, what's the magnitude of v? Well, I can calculate it, or I can just see that it's just going to be 2, because it has only one component, so I know how long it is. But if I calculate it, it's just going to be 0 squared plus 2 squared, which is the square root of 4, which is sure enough 2, just as I would have guessed. Okay. So then, u is equal to 1 over the magnitude of v as a scalar times v, which is just going to be equal to 1/2 times 0I plus 2j. I'm writing in the 0 here just to make it clear, and essentially you can just think of it as just distributing. And this is just going to equal 0 plus 1j. Which just equals j. Okay, so here you see actually again what the meaning of I and j really are. They are the unit vectors that are specifically the pointing in the direction of the y-axis or the x-axis. And so here, I actually, if I were paying close attention to what everything means, I would actually be able to answer that question without any calculation whatsoever. I would know that this vector was going in a positive y direction, and I would know that the unit vector that goes in the positive y direction is j. But then sometimes it's not quite so straightforward, like what if it is something like this? V equals, and let's say 12I minus 5j. Well, the magnitude of this, we recognize these numbers, 12s and 5s. They are part of a famous Pythagorean triple. But we don't have to recognize it, we can just calculate it. -5 squared. And so it's going to be equal to square root of 144 plus 25, which is the square root of 169, which, as I already mentioned, happens to be a perfect square. So this equals 13. Okay. Then that means u is equal to 1 over the magnitude of v times v, which is just going to be 1 over 13 times 12i minus 5j, which is just going to be, if we go component by component, 12 over 13i minus 5 over 13j. One of the great advantages of the ij notation is that the vector addition or scalar multiplication is really actually just a matter of distributing or combining like terms. It just actually fits in quite nicely with ordinary algebra. Okay, and then let's see what it's like in the worst case. So this was nice because it was a perfect square, the magnitude of v, but it might not be. Let's say v equals something like -4i plus j. So it might not be something as friendly as that previous result, but our approach is not different. Just the arithmetic gets a little bit more involved. So we have -4 squared plus 1 squared. Square root of that is going to give us the magnitude. And that's going to be square root of 16 plus 1, which is, in other words, the square root of 17. Well, that's not a perfect square, so that's as far as I can go on that side. And then u is going to be 1 over the magnitude of v times v, which is going to be 1 over root 17 times -4i plus j. And we know what this is going to end up being. This is going to end up being something that we're going to have to rationalize. Oops, 17. -4 over 17i plus 1 over root 17j, or -4 over root 17, which we have to rationalize both of these denominators, and they rationalize the same way. Multiply the top and bottom by root 17. And the same thing will happen over here. Multiply the top and bottom by root 17. And you'd have those. Okay. So, note, just as we found the magnitude by using the same technique as for polar coordinates, we can find the angle in the same manner. We can also find the angle a vector makes with the positive x-axis. In other words, its angle in standard position, i.e. in standard position, by using the same techniques as for polar coordinates, or for that matter, for complex numbers as well. A lot of the same things that we've been doing here would be very similar to how you do them for complex numbers also. So tangent of theta is equal to b over a. That's if v is equal to the usual ai plus b times the component vector j. So then tangent inverse of b over a plus possibly an adjustment for the quadrant. So in other words, add 180 or subtract 180 if that's what you need to do in order to get yourself into the correct quadrant. We can also go the other direction and find the components if we are given the magnitude and direction. So this is called resolving the vector into its components. And this is the usual way a lot of calculations are done in physics. All right. In particular, if magnitude of v corresponds with r and theta is the angle, v equals ai plus bj, where a equals r, or as we write it now, magnitude of v, cosine theta, and b is equal to magnitude of v, so in other words the r, times the sine of theta. So sometimes we write v equals magnitude of v cosine theta I, magnitude of v sine theta j. All right, let's practice both of these directions. So one where we have to find the components, and the other where we have to find the angle. So example, write the vector. With the given magnitude and angle, in the form v equals ai plus bj. All right. So let's say we had something like this. Magnitude of V was told to us to be 8. And let's say the angle, which in the Pearson they use alpha. There's no reason not to use theta instead, but they use alpha, so I'll just write it like that. Alpha equals 45 degrees. All right. Well, if V is supposed to equal AI plus BJ, it means A is playing the role of X, B is playing the role of Y. So A is equal to the magnitude of V times cosine, here of the alpha, it's been called. B, on the other hand, is equal to magnitude of V sine alpha. So that's going to equal 8 times cosine 45 degrees. And this one is going to equal 8 times the sine of 45 degrees. But 45 is famous. We all know the cosine and the sine of 45 degrees. It is root 2 over 2. And both of these can be reduced in exactly the same way. They cancel a little bit there and there. And it makes a 4 and a 4, 1 and a 1. And that just gives us 4 root 2 and 4 root 2. So then V equals 4 root 2 I plus 4 root 2 j. What if what we have is something like this? Magnitude of V is going to be now 15. And the angle, alpha, is going to be 315. Well, once again, my default setup here, V equals AI plus BJ. A is the magnitude of V cosine alpha. B is equal to magnitude of V sine alpha. 315, that's 45 degrees short of a full circle. So that's going to put us down here. So it's going to be 15 times the cosine of 315, which is going to be positive root 2 over 2. Here's going to be 15 times the sine, which is negative root 2 over 2, which is just going to be not really reducible, so we'll just write it like this. Negative 15 root 2 over 2. And so then V would be expressed as 15 root 2 over 2I minus 15 root 2 over 2j. So this direction, just as it was for polar coordinates and just as it was for complex numbers, is the easier of the two directions because you don't have to make any adjustments for the quadrant. You just have to do whatever the sine or cosine tells you. Now, an alternative version of this, when we turn it around, we can be given the vector in its component form, and we can ask for its direction. So find the angle for V. And by angle, by default, we're going to mean standard position unless we have some reason to vary that. All right, so V here we'll start with just I. Let's make it actually negative I minus square root of 3j. All right. That means A equals -1, B equals negative root 3. So then tangent of theta is going to equal negative root 3 over -1, which is just going to equal positive root 3. So at first, you might be thinking, oh yeah, tangent equals root 3. You might be thinking about, okay, I know that one, that's 60 degrees. But wait a second here. We know that this is negative and negative, so this is going to be in quadrant 3. So -1, -3. So it's in quadrant 3. So what that means is we don't want the 60-degree angle that we usually would want here. We want the one that's down here, which is 240 degrees. So this would have been 60 degrees, but it's the wrong quadrant. And this is what the inverse tangent would have given us. So this is 60 degrees plus 180. Just to get us to the other side so that we're in the correct quadrant. Okay. And then, so that one was one of our familiar friends. It was just a nice classic angle. Oh, and I should note here. Note the MyLab. MyLab homework. We'll want an angle between 0 and 360 degrees. So as an example here of where this comes into play, so it doesn't really matter that much in practice for us, but if you're trying to do your homework, MyLab has its own way of how answers need to be formatted, and so it is up to you to satisfy their requirements. And that will come up in, for example, something like this. So let's say we have V equals 6I minus 4j. So again here, it's always a good idea, think about quadrants. So it's going to be in quadrant 4, so positive x, negative y. So it's going to be over here. So quadrant 4. All right, so A equals 6, B equals -4. So the tangent of theta is going to equal -4 over 6, in other words, -2/3. So if I take the inverse tangent of that, and if my calculator is in degrees, then what I will get will look like this. So my calculator is currently, it turns out, in degrees. Always check, make sure your calculator is in the mode that is appropriate for the problem. And if I do the second inverse tangent, -2 divided by 3. So I get -33.69, or the MyLab will want you to round to 1 decimal place. So I'll go 0.7 degrees. And that is the correct value. I can see from my sketch here, that looks about right. However, so it's not even in the wrong quadrant, it's just in the wrong format. The format is supposed to be between 0 and 360. So just think about it. So over here, so negative 33.7 degrees plus 360 degrees will get us back to that same spot. We're not in the wrong quadrant, it's just the wrong format. So we just take this answer plus 360, and that should get us to the right version of the answer. So 326.3. And again, this is actually just pickiness on the part of my lab. It's not, this is not a sort of adjustment we would typically have to make in ordinary math. It's just in order to allow the computer to judge our answer correctly, we need it to be in a form the computer can understand. All right, now last one here, let's go with v equals negative I plus 3j. So once again, quick sketch of where the quadrant is here. So we're in quadrant 2. Good to know. Okay. So a is negative 1, it's the coefficient of the I. The b is 3. Well, then the tangent of theta is equal to 3 over negative 1, which is just equal to negative 3. And if I take the inverse tangent of that, then what I get is negative 71.6 degrees. And I can see that's going to put me down here, wrong quadrant. So theta is going to be that plus our adjustment, which here the adjustment will be 180 to get us to the other side of the circle, which is the correct quadrant. And that'll also give us the answer that's between 0 and 360, so my lab will be happy. So we just take our previous answer and add 180. So it's 108.4 degrees. So that's how we can evaluate those sorts of things. Now, the last phase of this is like the last phase of so many sections is applications. And let's first discuss what the sort of applications we're going to have to deal with will be, and then how we will approach them. So applications. We will frequently encounter situations in which vectors representing, for example, force, for example, are combined. Our approach is going to be to, almost all of the time, resolve the vector into its components so then we can add. Resolve all vectors into components. Which we can then add. Okay, let's start with something relatively easy, something that doesn't involve multiple forces, but just one force, but it's at an angle. So, example. Force vector. Let's say a wagon, like a toy wagon. Is being pulled by a force of 30 pounds. So pounds, you're most familiar with that probably as a measurement of weight, but it actually is any kind of force, and this would mean it's the equivalent of basically like a 30-pound weight attached to maybe like a pulley, and it is pulling the wagon along. Applied at an upward angle of 60 degrees. So this first one, our task will just be express the force vector F in terms of I and j. So for our first task here, we don't have to add any other forces. We just want to see if we can resolve one single force into its two component vectors. All right. Well, let's think about this. So a force of 30 pounds, that represents the magnitude. And the angle here, sometimes you just want to do a quick sketch to make sure it makes sense. The angle here is the angle that the force is being applied, 60 degrees, this diagram is not to scale. And so is it really 60? Yes, it is. Sometimes we'll have to be a little bit more sophisticated in how we treat the angle, and we'll have to figure out relative to some other thing what's going on, but here it is straightforwardly just 60 degrees. Again, not to scale. We draw it better to scale. There's a force of 30 pounds, and it's being applied obliquely at an angle. Okay. Well, A is just going to be that 30 times the cosine of 60, which is 30 times 1/2, which is just going to be 15. B is going to be 30 sine of 60, which is going to be 30 times root 3 over 2, which is just going to be 15 root 3. And so what that would mean is the force is just equal to 15I, so that's the horizontal component of the force, plus 15 root 3j. And notice the horizontal component is the smaller one because we're pulling it more up than we are to the side. And so this would be, we would be applying more pressure upward than we would laterally to this particular wagon. Okay, so that's how that would go. Now let's see how it can play out if we have multiple forces all being applied together and we have to resolve those. Okay, so next example here. So this is a resultant vector, or a resultant force. So two forces. So two forces of magnitude 40 newtons. So newtons is the standard international measurement of force. And 50 newtons are applied together at the angles indicated. So here, I'm just going to draw us a diagram. Picture's worth a bunch of words. So we're going to have the degree of, we're going to have the magnitude 40 Newton force. It's going to be at an angle of 45 degrees. So this is F1. And that's going to be the 40 Newton force. And it's going to be at an angle of 45 degrees positively like that. And then we're going to have another one, the 50-degree force, which is going to be applied at a 30-degree angle. And I'll even write it negative 30 degree like that. So of course, in practice, you have two different forces being tugged on it. Neither direction is necessarily positive or negative, but we can orient it so that we can call that angle negative, that angle positive, and then the question is, find the direction and magnitude of the resultant force. And resultant force here means the combined force. So i.e. find F1 plus F2. So that's what we really want to do. Okay. Well, we'll just break it down into two pieces. F1. So the magnitude of F1 equals 40, and theta 1 is equal to 45 degrees. So that means that that I'll just call them A1 and B1. A1 equals 40 cosine 45 degrees, which is equal to 40 times root 2 over 2, which is then going to just equal 20 root 2. So good. And B1 is 40 cosine, sine, I mean. Not that it really matters this time, but other times it will. Cosine and sine of 45 degrees, of course, are the same. 40 times root 2 over 2 equal to 20 root 2. Okay, so F1 has been resolved. F1 equals 20 root 2 I plus 20 root 2 j. Now, f2. So first off, the magnitude of f2 is equal to 50, and the angle is equal to negative 30 in standard position. So a2 is equal to 50 cosine negative 30 degrees, which is just going to equal 50 times the cosine of 30 is going to, of negative 30 is going to be root 3 over 2. It's going to be then 25 root 3. B2 is going to equal, then over here we'll have 50 sine negative 30 degrees, which is equal to 50 times negative 1/2, which is negative 25. So the vertical components here are both positive, and what that means is they're adding together. So the horizontal components are both positive, means they're going to be adding together. And the vertical components are opposite, and what that means is they will be canceling each other out to some extent. So, sorry, 25 root 3 I minus 25, just j. Just j. Okay, well then, to find the resultant force just means to add those two together, component by component. So f1 plus f2 just means add the I components together. So it's 20 root 2 plus 25 root 3. And the j components would also be combined. 20 root 2 minus 25 on the j. All right. Well, now, if this were, so now what we would probably want to do is find decimal values of these, because these numbers are a little bit ungainly, awkward to work with, and so what we'll do is just plug these in. So 20 times root 2. Actually, no, I shouldn't do that by piece. I should do it all together. 20 root 2 plus 25 root 3. And that's going to be 71.59. I'll leave it as unrounded as I can for the earlier stages and only round finally at my absolute end result. And then the other one, 20 times root 2 minus 25 would be 3.28j. All right. So direction and magnitude. So this is in quadrant 1. We can see because they're both positive. One's really positive, one's slightly positive. So the tangent inverse will work out just fine for us. And so what we'll get is an angle (3.28) divided by 71.59 of 2.6 degrees. So it's only very slightly positive. Otherwise, it would be directly to the side. So the two forces, vertical components, almost cancel each other out. And so it's almost entirely horizontal. And as for the magnitude of the combined forces, the easiest thing is to just take our results and put them in the formula. And just evaluate it all in one step in your calculator. Okay, so that's going to be square root of. I don't need the parentheses on the inside here that I wrote. We just write those whenever we have decimals to avoid misreading. The only time the parentheses are really necessary is if there's a negative on these types of calculations. And we get 71.7 newtons. All right, so that's how you can combine two forces in that form. Now, one more context in which we will find ourselves adding vectors and such is going to be when we are talking about the bearing of an airplane. So speed and direction of an aircraft. All right, the setup is we have a plane. A plane goes due west with an airspeed of 500 miles per hour. The wind is blowing southeast at 100 miles an hour. So what we can do is we can take this piece by piece. Step 1. Express the velocity of the aircraft relative to the air. Express V A the velocity of the aircraft relative to the air, and that's what the airspeed represents here, and VW the velocity of the wind relative to the ground. Both in the form AI plus BJ. So both in terms of the components of their unit vectors. Okay, well, first off, most important thing is, so north, east, south, and west. All right, so draw yourself a little compass first off. Okay, so the plane. So we can actually see right there that this is actually just going to be directly west. So that's just going to be negative 500i. So the compass, if we translate it into i's and j's, we can see that the east is just going to be I, west will be negative I, north will be j, south will be negative j. So we actually can do that just straightforwardly like that. So the angle is 180 degrees, which is nice, and so we don't even need to do anything too crazy there. As for the VW though, that one we have to work for a little bit. So what we know is the magnitude of it. The problem with the VW is that it is it's going at an angle. And we know that the magnitude of it is 100, and we know that the angle that it makes, so we have to think about where it is negative 45 degrees. Okay. Well then, it's A. So A for the wind will be 100 cosine negative 45 degrees. And the B for the wind will be 100 sine negative 45 degrees. And then what that's going to lead us to is equal to 100 cosine of negative 45 is root 2 over 2. In other words, 50 root 2. And sine of negative 45 is going to be negative root 2 over 2, which will give us negative 50 root 2. All right, so then that means that the velocity of the wind is going to be 50 root 2i minus 50 root 2j. Okay, so we've got the two pieces. One was easy, one we had to work for. And now for B, let's say we have to find the velocity of the plane relative to the ground. So the velocity means the vector, and relative to the ground means not like we already have its speed through the air, but rather its speed relative to the actual ground. All right, so in other words, we have to take the speed through the air plus, or we have to take the velocity through the air plus the velocity of the air to get the overall velocity, i.e. find VA plus VW. Okay, well, we already have all the pieces that we need for this. This is going to be actually a pretty straightforward one right here. So it's going to be the I components, negative 500, which is what we found for VA, plus 50 root 2, the I. And then for the J component, we're going to have negative 50, negative 50 root 2. There was no j component on the airplane, just on the wind. Okay, and then approximately speaking, let's just figure out what those are. So that is negative 500 plus 50 times the square root of 2. So that's negative 429.3 to the I, and then negative 50 square root of 2. That's equal to negative 70.7 j. So depending on how we are asked to round, this would be the velocity. And then part C, find the speed and direction. Speed and direction. Relative to the ground. i.e., the magnitude and the bearing. Okay. So the speed. So this is the magnitude. Which is our previous answer put into the Pythagorean formula there. So square root 429.3 squared plus negative 70.7 squared. And again, we will just use, just put it all in the calculator in one expression. So the way this one expression is going to look, so we can see it better. So it's going to be square root 429.3 squared. I'm just, by instinct, I know that if I go around putting extra parentheses and negatives, that's going to be more trouble than it's worth. It's just going to possibly lead to a mistake. Plus 70.7 squared. And I get 435.1. Which is, you'll notice, slightly slower, or it's quite a bit slower than the actual airspeed of the plane, but that's because the plane was going against the wind. Now for the direction, we're talking about something that's going to be in quadrant 4, or sorry, quadrant 3, I mean. So quadrant 3. So I know that my inverse tangent isn't going to necessarily work here, but I'll at least calculate it. And then I'll figure out what I need to adjust. So negative 70 over negative 429.3. So first, the inverse tangent here. Negative 70.7 divided by negative 429.3. So I get 9.35 degrees. So let's say 9.4 degrees. If I round to 1 decimal place. Well, that's clearly wrong. Wrong quadrant. So then, So then my actual theta here is going to be, is actually going to be 180 plus that, or that plus 180. So 9.4 degrees plus 180, which is 189.4 degrees, which will put us in quadrant 3, which is where we're supposed to be. So that's great. That's the theta. However, that's not actually a heading or a bearing. So to put it into a bearing or a heading, same thing basically. So heading. So remember, the heading has to go north something, west or east, or south something, west or east. And you go from whichever is closest, and you tell how far you have to go in the direction of the other angle. So this would be, so we'd be talking about the angle 9.4 degrees off of the west. So if that's 9.4 degrees, then that means this would be 80.6 degrees. And the way this goes is, remember it's south, 80.6 degrees, and then you say in which direction, and you say west. South, 80.6 degrees west is the way you say this. So remember, north or south, then how far off of north or south, and then in what direction. And then one last thing, note. In some applications, namely, there's going to be one big one in your homework. You'll need to start by changing the direction given from a bearing or a heading to an angle. In standard position. So for example, let's say we had a very similar problem. An airplane has an airspeed of 500 kilometers per hour and a bearing of north 45 degrees east relative to the wind. And the wind has a speed of 60 kilometers per hour and a bearing of north 30 degrees west relative to the ground. Then if we wanted to repeat the same problem, we want to repeat the steps from the previous problem and answer the same question, then our very first step is going to have to be to convert the bearing into an angle. So first, the bearings into angles. So for the aircraft, north 45 degrees east. That means 45 degrees off of north in the direction of east. And so that would mean that theta for the A would be 45 degrees. For the wind, north 30 degrees west. So it's from north, it's 30 degrees off in the direction of the west. So what's that mean this theta is going to be? So the theta for the wind is going to be 90 degrees plus 30 if we want to put it in standard position. So it's 120 degrees. So you have to interpret the bearing and turn that into a theta. And then the rest would proceed as above. So then we can proceed to find AA, BA, AW, BW as before. But this video has gone long enough, and so we'll have to end it there. You can fill in the dots for yourself. All right, well, that'll do it for this episode of Math 112. See you next time. Till then, bye.